Get this book is packed with mind-blowing math concepts.
It's refreshing, really. It doesn't shy away from the complex stuff. It tackles that space between how we see the world and the abstract stuff mathematicians ponder.
Yeah. Math can seem intimidating, but this book flips the script. Reminds us that math is woven into the fabric of reality, like a hidden framework holding it all together, ready for some aha moments.
Absolutely. And it starts by asking, what if we could hit undo on reality? Strip away everything we see and touch.
Whoa, okay. No trees, buildings, planets, not even atoms. Like hitting the ultimate reset button. Nothingness, right?
Not quite. The book suggests what's left is the language of math itself. It proposes that math isn't something we invented, but something fundamental to the universe, like a blueprint extending beyond our perception.
So instead of atoms being the universe's Lego blocks, it's more like math is the instruction manual for how those blocks connect.
Precisely. The book uses this great story about Einstein and David Hilbert. Einstein, with his theory of relativity. Well, Hilbert, a brilliant mathematician, published similar equations around the same time.
And Einstein, he was all about the equations themselves. But Hilbert, he saw them differently.
Right. Hilbert was obsessed with the core principles, the axioms behind all mathematical truths. He thought maybe these principles could explain not just relativity, but every physical theory out there.
Talk about ambitious. Like searching for a master key to unlock every mystery in the universe.
Yeah. While there are limits to what we can actually prove within any system we'll get to, that the point is, these abstract math ideas, they might have implications we haven't even begun to grasp.
Okay, now we're talking. So let's shift gears to something else that bends the mind a bit. Higher dimensions.
Right. We experience the world in 3 dimensions: length, width, height.
Pretty impossible to truly visualize a 4th dimension.
Like explaining color to someone born blind. But here's the key. Mathematicians, they don't rely on visualization. They explore higher dimensions through equations and logic. The book uses a circle and a sphere to explain.
A circle being like a one-dimensional sphere, you mean?
Right.
Where you can only move along the circumference like a line looping back on itself?
Exactly. And a sphere, a typical ball, is a 2-dimensional sphere because you can move across its surface in 2 directions. Now think about that logic. What would a 3-dimensional sphere be?
It would have to exist in 4-dimensional space.
Whoa! We can't picture it, but we can describe its properties, right?
Exactly. Things like this hypervolume, which is like volume but in 4D. The book also mentions a tesseract, a 4-dimensional cube with 16 corners, 32 edges, 8 3D cubes as its cells. Wild stuff.
Wild is an understatement. And there was this guy, Charles Hinton, obsessed with the 4th dimension back in the 1800s. He even invented a baseball pitching machine trying to show these concepts. It was deemed too dangerous, but still. His fascination with higher dimensions, it makes you wonder, are there things beyond our perception, like seeing a new color for the first time? Reminds me of Claude Monet. After cataract surgery later in life, his paintings became much more vibrant, almost like he was seeing ultraviolet light, something we can't naturally see. It's amazing to think our senses might be limiting our experience of reality, both physically and conceptually.
And maybe math is the key to unlocking those hidden dimensions, to see what lies beyond our normal perception.
For the longest time, randomness was seen as this mystical thing, like beyond math's grasp.
It's true. We love pinning meaning on random things, like
Yeah.
some sign from the universe or something.
Right. But as math grew, we found a way to understand these chance events through probability.
Exactly. And once you view randomness through that lens of probability, it really challenges those common assumptions we have.
Totally. Like the book talks about winning the lottery twice. It might not be as crazy as we think.
Oh, I remember that. You're saying that while the chances of one person winning twice are tiny, the probability of anyone winning twice over time with enough people playing is actually much higher.
Yeah. It's all about perspective. We fixate on the individual, but zoom out. The bigger picture, the odds shift big time.
It's humbling, isn't it? Like maybe we're not as unique as we like to believe.
There's beauty in that, though, right? The universe, it operates on its own terms, and sometimes those terms involve some good old chance. Speaking of, the book dives into this fascinating example, pi, and the randomness, or apparent randomness, of it.
Ah, pi, 3.14159. Going on forever, we've all tried to memorize those digits. What does it even mean for them to be random, though? Pi is a fixed value, isn't it?
It is, and that's what makes it so interesting. They've calculated pi out to trillions of digits, and the distribution, totally random it seems, 0 through 9, each digit popping up with roughly the same frequency.
Hold on. So it's this fixed number, unchanging, Yet its decimal expansion appears chaotic. Isn't that a paradox?
You got it, and that leads to the question, is it truly random? Mathematicians think pi's normal in base 10, meaning each digit appears equally in its decimal expansion. And maybe, just maybe, it's absolutely normal, meaning it's normal in any base.
But even still, those digits are already set, right? It's not like they're being randomly generated as we go. It's more like the distribution, the way they're spread out. That's what seems random.
Precisely, and it raises this big question. Those digits of pi that haven't been calculated yet, do they even really exist? They're not random in the purest sense, but they're statistically random to us until we actually do the math and figure them out.
Mind-blowing. It's like those digits are in some mathematical void waiting to be found.
Okay, shifting gears before my brain melts, the book talks about fractals, right? Those incredibly complex shapes repeating at smaller and smaller scales.
Yeah, you got it. Fractals, they have this thing called self-similarity. Zoom in as much as you want, you'll still see those same patterns playing out, just with less detail. The book uses measuring Britain's coastline as an example.
Oh, right. If you're using a map and a ruler, you get a certain length. But get a more precise tool. Start measuring every little bend. That coastline seems to get longer and longer. And theoretically, that could go on forever, with the coast approaching an infinite length. Fractals have this wild property. Non-integer dimensions.
Wait, I thought dimensions were always whole numbers. 1, 2, 3. How can you have a dimension of like 1.58?
It's a brain bender for sure. It all comes down to how these shapes scale when you zoom in. The book talks about something called box counting, a way mathematicians calculate the fractal dimension of an object. What's wild is that nature uses fractals too.
The human lung, right. With that network of air sacs giving it a huge surface area, it's like cramming a 3D structure into a smaller space, like the book said.
Perfect example of how evolutions use fractals to optimize things. And it gets even cooler when you bring in chaos theory. Heard of the butterfly effect?
Classic. A butterfly flaps its wings in Brazil, causes a tornado in Texas, right?
Exactly. Shows the heart of chaos theory studying systems crazy sensitive to their initial conditions. The tiniest change at the start leads to massive differences down the line.
So even if we knew all the rules of a chaotic system, predicting its long-term behavior perfectly is basically impossible.
Yep. And here's where it gets truly wild. Chaotic systems, they can create fractals. Like graphing certain equations can create these infinitely complex and beautiful shapes. It's like chaos is the driving force behind these intricate patterns.
That's poetic almost.
Mm-hmm.
Order from chaos. Which honestly sounds a lot like life in general.
Right. Speaking of things that make you think, the book also talks about paradoxes, those brain-twisting thought experiments that contradict themselves. You a fan of those?
Paradoxes, yeah. Total brain teasers. They make you question everything you thought you knew about logic.
Yeah, right. And this book, it dives right into them, saying they're not just fun thought experiments. Paradoxes can actually show us the limits of logic.
And sometimes even lead to big breakthroughs, right?
Exactly. Like there's that classic one, Buridan's ass.
Oh yeah, the donkey starving because he can't decide between 2 piles of hay. Sounds ridiculous, but it makes you think.
Totally. Shows how pure reason can stumble, especially with choices where there's no clear winner. And the book, it goes even deeper. Gödel's incompleteness theorems, for instance.
Okay, I've heard the name, but honestly, went right over my head. Something about proving stuff in math, right?
Basically, Gödel showed that in any complex enough mathematical system, which is most of them, there are going to be statements that are true, but you can't actually prove within that system.
Hold on. So there's stuff we can know is true, but we can never actually prove it using math. That's kind of freaky.
It's mind-blowing, honestly. It means even in the world of math, there are limits to what we can be absolutely sure of. And this isn't just some theory. It affects things like computer science, where some problems we might never solve completely.
Whoa, that's heavy stuff. Okay, maybe for a lighter turn, the book also talks about music.
Right. We often think of it as beautiful, harmonious, and turns out music's got deep roots in math, just like everything else.
Yeah, I remember learning about musical intervals as ratios. Like an octave is a 2-to-1 ratio, right?
Exactly. And when that 12-tone equal temperament scale came about, that was huge. It balances mathematical purity with, actually being able to play music easily in different keys.
So we created a system that sounds good to our ears while still following those hidden math rules.
Which then makes you wonder, if music has this mathematical basis, could alien civilizations have developed something similar?
That's a cool thought. If we ever meet any, maybe we can bond over some interstellar tunes.
Who knows? Maybe music is the universal language, going beyond even planets. But for now, let's journey to another fascinating concept: infinity.
Okay, here we go. Down the rabbit hole. A good place to start. prime numbers. Those are the ones only divisible by 1 and themselves, right? Like 2, 3, 5, 7. Always struggled to remember those.
Well, imagine trying to remember an infinite amount, because like Euclid figured out, there really are infinitely many prime numbers.
And the book talks about Goldbach's conjecture, right? Something about all even numbers being the sum of 2 primes.
Yeah, they've tested it with crazy big numbers, and it seems to work out, but no one can prove it for sure. It really shows how prime numbers, they might look simple, but they hide some really deep mathematical mysteries.
It's like we have this infinite set of numbers, and we're still figuring out the code,
Hmm.
which makes you wonder about infinity itself. And the book goes there, doesn't it? Different sizes of infinity.
It does. It's where things get really wild. We think of infinity as just one thing going on forever, but there are different levels, different magnitudes to it.
Okay, now I'm lost.
Yeah.
How can one infinity be bigger than another? That's like saying one forever is longer than a different forever.
I know it's a tough one to wrap your head around, but it has to do with the size of infinite sets. The book explains how all natural numbers, 1, 2, 3, and on, they have what's called Aleph null, basically the smallest type of infinity.
So Aleph, no, that's like the starting line. But how do you go bigger than that?
Think about all real numbers, not just the counting numbers, but also decimals, irrational numbers like pi. This guy, George Cantor, he showed that the set of real numbers is uncountable.
Uncountable? What does that even mean?
It means you can't pair up each real number with a natural number, even if you had forever. Cantor showed that real numbers are just too dense, too vast to match up one-to-one with natural numbers. So they have to have a bigger infinity, a larger cardinality.
So even though both are infinite, real numbers are, in a way, more infinite than natural numbers. This is blowing my mind.
And it gets even wilder from there.
Oh.
Mathematicians have come up with ways to describe numbers so huge they make things like the number of stars look tiny.
The book talked about Knuth's up arrow notation. Right? It starts with exponents, then goes to tetration, pentation. Each level basically explodes the number.
Exactly. It's how mathematicians deal with these crazy huge numbers that come up in some problems. And then there's Graham's number. It actually held the record for the biggest number ever used in a serious math proof.
I can't even begin to imagine a number that big. It's mind-boggling.
It just goes to show math is full of surprises. From the very foundation of the universe to these huge ideas of infinity and beyond, always something new to explore.
This deep dive has been incredible. If anyone listening wants to really have their mind blown, check out El sorprendente libro de las rarezas matemáticas. It's a fantastic exploration of the wonders of mathematics. Thanks for joining us on this incredible journey.